In this video, we will look at two of the classic recursive algorithms of computer science. The first one is known as the Tower of Hanoi program or problem. And I've got a graphic here. This image is taken courtesy of Khan Academy. And it shows the standard three-post game that I'm sure you've all seen at some point. And in this game, you have three posts, and then you have a number of disks that are all stacked on one post where no larger disk is on top of a smaller one. And the objective of this puzzle is to move all of the disks from the first post to either one or the other empty posts, and in so doing, never place one larger disk on top of a smaller one. And our objective here is to write a program that will do that, or at least will lay out all the steps for doing that. All right, well, let's see how involved this is going to be. Okay, so let's move the image out of the way. And here is the code. Close that part of the window. So here we have the code that will do that. At the upper part of the screen, that's just a description of what I just showed you, where the objective of the program is to move those disks from one post to another. It's a recursive program. We have a function, a recursive function that's called do towers. So let's scroll down to that function and look how short it is. Look how small. So in this case, this function is going to give us the moves that it would take to solve the problem. Inside here, and I'm not even taking the time to type in the code because it's so short, we'll just go through it one line at a time. So the function is going to accept the number of disks. So to begin with, you can have any number of disks that you want. Trivial will be 1 or 2, but from 3 upward, then it's more involved. Then the next 3 arguments are going to represent just some number that represents each of the posts. I'm calling these post X and post Y and post Z, but they just represent the 3 posts that we have in the game itself. Now, above this in the comments, I want to show you what's really going on with this recursive function. The result of calling the function is to move a disk from whatever post we put in this position here to whatever post we list in this position over here. So that's what each call to the function does. It figures out what move that's going to be. We have one if statement, so as long as we have a disk, then we have something to do. And within that, if the disks are larger than 0, we have at least one disk, then we have a recursive call that shows up at the very beginning. Now, notice that like other recursive functions, we have to have some way to exit the function eventually. So the recursive call will be the number of disks minus 1. So eventually we do get down to 0. We now have post X in its same position, but notice that post Z has been shifted to the middle and post Y is now on the far right side. So this call to the recursive function do towers is going to move a disk from post X to post Y in this case. So the positions matter. It's always moving a disk from whatever post we list here over to whatever post we list over here. And then the post in the middle is just our auxiliary post. It's our kind of a staging area from one to the next. Then we have a cout statement, and it just lists explicitly what the move would be for that particular disk and that particular post. Then we have another call to do towers, and in this one we're also calling it with disks minus 1. We have to eventually get out. And in this instance, notice that in the beginning post, that's going to be post Y, and the ending post is post Z. So this is going to transfer a disk from post Y, which is going to be the last post, as it turns out, and to post, well, I'm sorry, this post Y is going to be the middle post, and it'll transfer a disk from the middle post over to the last post, post Z. And that's it. That is all it takes to do this. So within our do towers recursive function, we just have two more recursive calls and a cout statement to print out the actual move that we need to make. And I'm counting how many moves is required, so that's all this thing does here. We've got a global variable for moves that I'll just increment, and then we return. Pretty simple. Who would have thought that such a simple function could solve this problem? In the main program, I have a global variable moves, so that will keep up with how many moves it takes for the number of disks that we have. We start out where you will type in how many disks you want. We read that in, and then we initiate the recursive calls by calling do towers from the main program with the total number of disks we have and the posts in regular order from left to right, 1, 2, 3. So that gets it started. The function itself will print out the actual moves required, and then once it's all finished, we'll print out how many total moves it took to solve the problem. So that's it. So this is a classic computer science problem that I'm sure you will have. Maybe you've seen it already. If not, then you will see it if you continue with computer science. Well, let's show how this works. Let's go ahead and run the program, and then we'll compile it and run it, and we'll see what we get. The program has compiled, and it is ready to go. How many disks do you have? The smallest number that makes sense would be 3. So that's typically what we start with. So let's put in 3 disks, and I hit enter. And then notice it prints out exactly which move we need to make. So think about this. We have disks on post 1, where disk 1 is the smallest, disk 2 is the middle-sized one, and disk 3 is the largest. So if you were to take out a piece of paper and kind of draw up this beginning situation, and then you followed all of these moves, then you would be able to solve the problem. So we move disk 1, that's the smallest one. We want to move it over to post 3. Okay, then we'll take the second disk off of post 1, that's the middle-sized one, and we'll put it in the middle post. Now we have one disk on each post. And now we will take disk number 1 off of post 3 and put it back over on post 2. So now we have disks 1 and 2 on post 2. Post 3 is empty, and the largest disk is on post 1. So then you just move it from post 1 to post 3. Then you take the disk 1 from post 2 and you put it on post 1. Okay, now that frees up disk 2, so there's nothing on top of it. So you can take disk 2 and put it on top of post 3. And then finally, you take the smallest disk from 1 and you put it on top of the disk on 3, and now you've moved them. So that solution, it required 7 moves. All right, now remember that. It took 7 moves to do 3 disks. Let's run the program again, and let's put in a larger number. So let me stop this one, and I'll run it again. This time, let's go up by 1. Let's go with 4 disks. All right, so now you can see we have a larger number of moves. So we have disks 1, 2, 3, 4 shows up down here. So it takes quite a few more moves, and in fact, it takes exactly 15 moves to do that. So previously, it took us 7 moves. This time it takes 15. So remember those 2 numbers, and let's try it one more time. So I run the program again. Let's go up to 5. And now the number of movements is growing and growing. And in fact, it says it takes 31 moves. So if we have 7 moves for 3, 15 for 4, and 31 for 5, then you can begin to see a pattern. And as it turns out, the number of moves required for a given number of disks is 2 to the n minus 1. Sound familiar? So if we only had 3 disks, then 2 cubed is 8 minus 1 is 7. And when we had 4, now we have 2 to the 4 is 16 minus 1, it gives us 15. And in this case we had 5. So 2 to the 5th is 32 minus 1, so that gives us 31. So we would call this the order of the algorithm. So it takes 2 to the n minus 1 moves in order to solve this Tower of Hanoi program. So I'll stop that. And here's the code one more time. Okay, so it's a very short program, but yet it's quite powerful. So this illustrates that recursion is a very powerful thing. You can get a lot done with a very small amount of code if you use recursion for some problems. All right, so that'll conclude the example for the Tower of Hanoi program. The next classic recursive program that you'll see in computer science is a program that will generate the Fibonacci series. If you're not familiar with the Fibonacci series, it's shown here in comments, and it is just the numbers 1, 1, 2, 3, 5, 8, and so on. And after the first 2 terms, then term number 3 and beyond is made up of the sum of the previous 2. So here the value 2 is equal to the sum of the previous 2 terms, 1 plus 1. Okay, the number 3 is made up of the sum of the previous 2 terms, 1 and 3, and so on. 5 is the sum of 3 plus 2, and so on. So each term is equal to the sum of the previous 2. So that's the Fibonacci series. And if you wanted to look into some of the applications of this, you'll find out that this Fibonacci series applies to a lot of natural things in the world, like spirals and things like that. So there's a lot of stuff associated with it. But our job is to generate the series using a recursive function. Like the Tower of Hanoi program, you can do this with a very small amount of code. So now the complete program is shown here. I have a function, this is called Fibonacci, that has just a single integer as its argument. And the Fibonacci function is shown here. Now, this function calculates the value of a given term. So it doesn't print out all of the terms from 1 up to n. It calculates the value of whatever the nth term is. So for example, if you wanted to know the 5th term of the Fibonacci series, you would send in the value 5, and this would compute the value for you. Inside the function, the terminating condition is if n is less than or equal to 1, then you just return the value for n. So that's how we get out. The recursive call is shown here at the bottom. All right, so when you call Fibonacci with some number larger than 1, then you get a recursive call. In fact, you get 2 of them. So this one, we are going to add up, and let me pick a number. Let's say 5. So if we call it with a value of 5, then we are going to add up the Fibonacci value of term number 4 plus the Fibonacci value of term number 3. So we add up the 2 previous terms, and those become the value of the current term n. Okay, so again, a very short function code-wise. So in this program, we are going to type in how many terms we want, and I have a for loop which will compute the value of each of those terms going from 1 up to the number of terms. The value of any given term is determined by a call to the function, which is happening right here. So I'm just going to print that out. We'll set the width to 5 to give us room between numbers, and then we'll call the Fibonacci recursive function to print out the value for that term. I've added this little if statement in here so that we can print the terms across the screen left to right up to 10 terms per line. That's all this statement does. Then that's it. We terminate the program and we return. So that's all we need to do to calculate the Fibonacci series. So let's build this program and do a couple of examples. So we'll start it compiling. And we have the result. The window appears. How many terms would you like to see? Well, let's pick 6. Let's print out the first 6 terms of the Fibonacci series. So here we go. The first 2 terms, I'm not sure if I mentioned it or not, you always have to have the first 2 terms defined, because you can't add the previous 2 terms to get the value unless you have the first 2 terms. So it's always 1, 1, and then we can add to get the remaining set of the Fibonacci series. So these are 6 terms, 1, 1, 2, 3, 5, 8. Well, let's run it again and put in a larger number. How many terms would you like to see? Let's go up to 10. So here we go. You can count them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you can see the Fibonacci series from 1 up to 55. So let's do one more. Okay, let's try 20 this time. If the numbers get too big, they'll be sort of run together. So here we go. So those all are 4 digits or less, so that's okay. So here are the first 20 terms of the Fibonacci series, where we wrap around, and 89 is the 11th term, and then 6725 would be the 20th term. So that's it. This is another classic recursive program example that shows you how to generate the Fibonacci series. So there are two classic recursive programs, and that's all I wanted to show you. So we will terminate the video at this point.